Okay, thank you very much for inviting me. So my name is Frank Zwaan, and what I'm going to present today is a result of a collaboration with plenty of people that have helped me a lot to get to this point. And what you can already see here is a couple of modeling results, numerical modeling results, in which I try to understand how mantle rocks are being serpentinized, which can lead to the production of hydrogen gas. And the idea behind this would be that we can harvest this hydrogen gas as a green energy source. So there is also a lot of logos at the bottom here with all the different institutes. And let's jump right into this. Oh, by the way, this is in inverted rift basins. So we open a rift, and then we close it again. We try to see what happens. Let's see if we can get to the next slide. Okay, so the motivation is really hydrogen gas that we can use for a green future. And so we all know that hydrogen is a very clean and nice fuel. If you have hydrogen gas and you burn it, then you get energy and water. And so there's no pollution at all, which is perfect. So we could have a green, clean world in the future. But there is a bit of a problem with this idea because we still need to get the hydrogen from somewhere. And that means that at the moment we are producing it, we are synthesizing it. And this is a very costly process. We need a lot of energy, and depending on the type of energy that you put in there, so fossil fuel with some carbon storing and capture, or perhaps even green energy, you still have to put in a lot of energy to get your hydrogen. So it's not very ideal. In fact, hydrogen is not really a source of energy, but it's a carrier of energy, and the energy comes from somewhere else in this case. But there seems to be also an opportunity to find hydrogen in nature. So various companies at the moment are looking for hydrogen deposits or concentrations that could be exploited in nature instead of having to produce it. So, and this is really something that has been picking up pace in the last years. And this is also a reason why I'm doing this project, because we really want to know how this works. There are various sources of natural, what we call natural hydrogen. For instance, there is radioactive decay, which can affect water, split water. There are also bacterial processes, and there is a whole host of other processes. But the most promising seems to be serpentinization. Serpentinization is very simply a reaction between olivine or pyroxene minerals with water to produce serpentine and hydrogen, as you can see here to the right. So it's a very simple way of thinking about it. There are a couple of more reactions that can happen, but in principle, if we put these minerals together with water, then we can get free hydrogen. And these rocks, we all know, are very common, or these minerals are very common in mantle rocks, for instance. So we are lucky, the Earth has plenty of mantle, but there is a bit of a problem there. That is that the mantle is often very deep in the Earth. So if you look at a cross-section of the Earth, let's say here, there would be first something like 30, 40 kilometers of crust, or continental crust, before you get to that mantle. And that mantle then has no water at all, or at least no fluid water. So we need to somehow get that mantle closer to the surface where it can react with surface water, and we need to understand how that works. So there are two tectonic regimes that can allow the exhumation of mantle. The first one would be rifting and hyperextension, when we break up a continent, and then we can get the mantle very close to the surface, where then the water is available to produce to do the serpentinization and hydrogen production or generation. And the other one would be that you can close one of these rift basins again, and then pieces of mantle rock can be pushed up into your origin, and then they can also serpentinize and produce hydrogen. So these two ways are what we are looking at here. So first opening and then closing of basins. Now, this can be simulated by using numerical models. For instance, this is a picture that Sascha Brune gave me at the start of the project. And we can use software like Aspect to do this kind of thing. And I proposed a project to go to Potsdam to exactly do this kind of thing. So I was lucky. I got this Discovery Fellowship, and now that's the reason I'm here in Potsdam and telling you this story. But there is a little bit of background that I wanted to share with you, because I didn't start with numerical modeling. I used to be someone who was playing with sand in the laboratory. I was an analog or a physical modeler. So you can see me here at the start of my PhD at the University of Bern in Switzerland, and later on during a postdoc in Switzerland as well. So I seem to be quite happy with all the sand and the machine that I was using to deform the sand and silicon layers that then reproduce tectonic deformation. And that's the reason that I do this, I think, is because I'm from the Netherlands, from the coast, and we have a very sandy beach. This is the little village I'm from. We have this very nice sandy beach, and I was always playing on the beach with the sand build and sandcastles and all those kind of things. So that maybe infected me with the the love for sand, let's say. And then I went on to well, this is not a picture of me, but it could have been me. But yeah, building these kind of structures, playing with the water and the sand. This led me to go to the university. And then when I found out that you can actually reproduce tectonic processes using sand layers and silicon layers, etc., in the laboratory, like what is shown over here during a master project, I did this cross section. I was really excited about this, and I really wanted to do a modeling of tectonics with this kind of methods. Um, this is one of the more recent works I did in Bern, where I tried to build lithospheric scale models. It's quite tricky. You need to have multiple layers all floating on top of a fluid. And the nice thing about this model that we developed in Bern is that you can put it into a CT scanner and you can look on the inside of this kind of model. And so I just wanted to show you a little bit what it looks like before we go to the numerical models. So this would be one of these models, a rifting model, in which we develop basins. So there's a kind of a double graben system developing here that's seen from the top. But you can't see what's going on in the inside with all these different layers that I mentioned before. But you can do that with a CT scan. And so this is a lithospheric scale model in which we have an upper crust made of sand, a lower crust made of silicon, an upper lithospheric mantle made of sand again. So the sand represents material that breaks, so brittle material. And the silicon represents ductile material. So it's brittle, ductile, floating on an asthenosphere layer, which is a syrup. So we use very peculiar materials. And then you can have a look at how this deforms over time. And a nice thing that you can already see here is that the mantle layers, they start to rise towards the surface. So we get mantle exhumation in this rift system, in this asymmetric rift system in this case. There's another part of this model where you can have a symmetric system. We still have mantle exhumation, but we get two grabens at the surface and some kind of shear in between these blocks here. And this way you can try to understand from a physical point of view, let's say, what happens in this kind of models. And then you can make nice pictures like this in 3D, where you can have oblique extension and en echelon graben structures and whatever you want. This looks all very nice, but the problem is that we can't do any things with temperature, and we can't really go very far with extension. So this is not applicable to the problem that I'm tackling nowadays with the computer models. So I switched sides. I went from the laboratory to the computer, and I had a hard time at the start. It's pretty tough to change your expertise. And I wrote a little blog about this. If you're interested, you can read about all my pains and all my suffering. But in the end, I'm quite happy to have made this step to the numerical world and to get very nice results, I think, out of the models. So now we can move to the computer part of the numerical models that I have been doing. So I'm aiming to study this mantle exhumation processes, and I'm using Aspect and Fastscape for that. So Aspect is the geodynamic code, which in this case here is 2D, where we have an upper crustal layer, a lower crustal layer, a lithospheric mantle layer, which is all on top of an sublithospheric mantle or the asthenosphere. And then we can extend this by stretching by pulling on the sides to get rifting, and then we can also compress it again to get inversion, so basin inversion. So you open a basin, you close a basin. You can even call it an accordion model if you want. And this is based on the work by Neuhardt et al. which then also involves surface processes. So there's the aspect has been coupled to Fastscape, where you can have a quasi 3D surface where you have your your surface processes active, which looks pretty nice, I have to say. And importantly here, we also have temperature effects, which could not be done in the previous analog models, or at least very different. It would be very difficult or very challenging. I can show you a little bit what a model like this would look like. So it's a very clean way of showing it. We have our topography for Fastscape, we have the aspect model, and then you can see how all the model starts to behave. We have here mantle exhumation, so all the green is rising to the surface during our rifting. Now we have a tectonic pause, nothing is really going on, and then we can see how the whole thing is being pushed together again. And most importantly, we have here a piece of green, a piece of mantle that is being exhumed or being preserved in this mountain range. So it's very close to the surface, and like during rifting, there would be potential for serpentinization and for hydrogen production. And importantly, the surface processes are very important to remove material so that the mantle can rise to the surface. If we don't have any erosion, then it will be very tough or impossible even to get the mantle up there. So it's a very important aspect of this kind of model. So we can have we can have a look at these models, and we can see that mantle material gets to the surface, and that's great. So yeah, we have a potential for hydrogen, but we still need to understand where the hydrogen actually is generated, and that's not just by we can't just say that by looking where the mantle at what point is. We need a bit more analysis. So the first step would be, okay, we have this exhumed mantle, but the second thing would be that the serpentinization process is most efficient between in a certain temperature window between about 200 and 350 degrees centigrade, which is shown here by these isotherms in this model. So that means that all the mantle, all the green part that is within this bound, and that's all shown here in this bluish color, that is in the right temperature to be efficient for serpentinization and hydrogen production. So that's where we have to look. But then, very importantly, we also need water to get this reaction going. Without water, there is no reaction. And we know that this is the case because if we look in origins, we often have fresh mantle rocks, so not unserpentinized mantle rocks close to the surface. And this can be explained by the simple fact that they never were in contact with water, because what we think is that we need large faults, large shear zones or faults, hopefully most likely active faults that open up, that allow water to circulate through the system. So that's what we also plot here in these figures, the gray and black. So the gray are faults, and in black, those are active faults within the mantle. And then the yellow part, that is where active faults are within the mantle, within this serpentinization window, this temperature range. So that's the yellow spots here. That's the places where we expect this serpentinization to be active, really active, and to produce the hydrogen. This approach here, we were inspired by Liu et al., who were looking at a similar problem, but in rifting. But we use the extension and compression cycle to expand upon their work. And this is what it might look like if you have a model. This would be rifting again, and I forgot to say maybe in the past and in the previous slides, but the orange here, that's sediments. So if you let it run, we again have the mantle rising to the surface, and then over there, you can see there's a little bit of yellow. Importantly or interestingly, we have hot material rising to the surface, which means that this temperature window, which is pretty large, if you want, in the undisturbed crust, it's getting very thin, and then we have a shear zone over here, which would allow serpentinization to occur. But it's fairly small, if you want, compared to what you might expect in another setting. And this becomes important later on. So now we have a tectonic pause, the whole system starts to cool, so we have this window getting larger. And then we start to compress, and you can see that we have larger yellow areas. So this is a combination of especially over here. There. Here you can nicely see that we have a larger, thicker, let's say, serpentinization window. We have large faults that are cutting through this mantle, and so this is a real nice place to expect serpentinization and hydrogen to be generated. So what we did in this study that we tried to publish is that we tried a couple of different parameters. So just to get a feeling of what might happen. And this is a model A, for instance, where we have a little bit of rifting, and then we close the basin again. And it's fairly obvious maybe, but if you only rift a little bit, there is not much mantle that's being exhumed. And then if you close the basin again, you get an origin that looks a little bit like this, like a pop-up structure. And there is not really an opportunity for the mantle to really get to the surface. There is a little blob of mantle here, but it's fairly deep. So you have a better chance if you have more rifting. So for instance, in this case here, we have 50 million years of rifting. There's a little post-rift cooling phase, but this is the model that you saw before, where we have plenty of mantle close to the surface, a little bit of serpentinization going on over here. And then if we close the system, then you allow for a large piece of mantle to get really pushed up into your origin. And then we also have these larger shear zones that affect the whole system. And then we have our serpentinization and hydrogen production. This is here to show what happens if we stop our deformation. So this is at the end of rifting. We have a couple of shear zones that are active. But then if we stop our deformation, according to our analysis, we don't have active faults anymore. So in principle, there is no serpentinization anymore because we don't open new faults. There is no circulation of water. So that's an assumption, but it's fairly clear in the model according to how we work. But you do get this cooling of the system, and that your serpentinization window gets way larger than it used to be before. So that's a good thing if you would like to produce hydrogen. And then there's another model over here in which we have a fairly similar situation as what we see here, but we have just more rifting. So you have a larger basin, and then you get a slightly different reactivation. But in the end, you get still a fairly similar asymmetric origin in which we can have a piece of mantle rising to the surface. And you see also that it's within the serpentinization window, hopefully this little bluish color. And also here we have more serpentinization going on. Now, these are nice figures, but we can also quantify certain things. So these are these three key models that we put in, that we like to, that we show in our manuscript that we try to publish, in which you can, for instance, measure or trace the amount of mantle that is being exhumed. In this case, we define exhumed mantle as material that has been put higher than the original base of the crust. And if you have a model where you have a little bit of rifting, so this is only 5 million years of rifting, we have some mantle exhumation, but not very much. And then if we start to close the system again during inversion, then most of the material is being pushed down again. So most of the mantle gets lost, or almost all of it. In the other model where we have more rifting, we have a very linear increase in the amount of exhumed mantle during the rifting phase. Then during this cooling phase, it's almost stable, although it sinks a little bit because there is some cooling going on, and we have some sediments being put on top, so the material sinks a little bit. But still, most of the mantle that's exhumed, that stays exhumed until you start to invert the whole system, and then it all goes down. But we do have still material that is preserved. So that's the material that you can see in green here being exhumed. This is the material that is very important and interesting. And we can also check the amount of material that's actively being exhumed. So that's the material that's moving upward. And that line is different from the total mantle exhumation. So there are pieces of mantle that are moving up and down. It's not just one homogeneous blob, but it's quite dynamic, and that's an interesting thing to see. And what we can also trace is the amount of exhumed mantle that's in the serpentinization window, and that also rises over time as the system is cooling down. your serpentinization window gets larger, and therefore there's more mantle in there. And you can also trace that over here. This is the other model where we have the same kind of pattern as over here, but to a larger degree. So we have more mantle that's being exhumed because we have a large basin. We still have this dynamic exhumation where parts of the mantle are moving up, other parts are down, still within this whole bulb. And we have way more material that's going into the serpentinization window. And then what we did was we could trace the amount of material that's being serpentinized, and that can be directly translated into the amount of hydrogen that could be produced in this kind of system. In black here for each of these models, it shows the production of hydrogen or serpentinization per year, and this is a logarithmic scale. So these are very small amounts. In this first model, there's almost nothing going on there. But in model B, we get to a certain level, which turns out to be some kind of a threshold if you look at the next model. So you go up to this certain threshold, and then it stays stable. That seems to be the stable amount of hydrogen production or serpentinization that we can expect in nature or in a rift system. But then if we start to invert, then we get suddenly a 20 times step in our serpentinization. It's not constantly 20 times higher, but it's fairly stable towards this upper end, especially in this model over here. So this is because we have this larger shear zones in a larger serpentinization window. And so that's a fairly good indication that we should potentially be looking for origins if we want to explore for natural hydrogen. What you can also see here is that this is the accumulation or the cumulative amount of hydrogen. This is not a log scale, but you can see how it suddenly starts to rise during the inversion phase. So there is some serpentinization going on during rifting, but then suddenly it starts to really kick off during inversion, at least in the models. It can be summarized in this picture here, just to recap everything a little bit. This is this last model in which we have first rifting, we have small amounts of serpentinization. The black line here shows that, and then at some point we get to this level here. But then if we go into inversion, you have this way larger areas that could serpentinize, and that's then 20 times higher, up to 20 times higher amounts of serpentinization and hydrogen production in principle. So if I summarize this, these are the different models that we ran. You can see it in the Wilson cycle framework if you want, where you start from rifting, you do first, well, you go maybe to the stretching or necking phase. You can go to breakup, and then it could even be post-rift cooling. So that would be the rifting cycle. And here we go into inversion. And at any step, any moment in time, you could go from rifting to inversion. So there's different pathways. And what is very clear, and it's summarized in this little graph here, but it's maybe clearer if you look at the little bulbs here of hydrogen, that we need a certain amount of extension before we get hydrogen generation in our rift cycle, in a rifting cycle. And then if we go into the inversion cycle, part of the cycle, then we should have a system where we have sufficient extension so that we can have sufficient, that we can actually have large amounts of hydrogen being generated during the inversion phase. An important thing that we should also think about is not only, okay, we have hydrogen, that sounds very cool, but we need to capture this as well. And for that, you would need something like a reservoir to accumulate it in. So if you think also about the type of sediments that you might expect in a rift basin, in a deep rift basin, you might think about, like shales or maybe some deep carbonates and fine material that's not a proper reservoir. It would be a good seal perhaps, but not a good reservoir. So reservoirs, as being what is really being written here, it's not very great in the deeper parts of a rift. However, if you go into an origin, there's plenty of sands and conglomerates, etc., around, and that could be a very good environment for accumulations of hydrogen to form in a similar way that oil and gas would form actually. And so together with the high amount of hydrogen production that we would expect, that's a really good combination. And this we can put in a little graph here, or a little concept of an orogenic hydrogen system, in which we would have in green here our mantle that's being exhumed close to the surface. There's this temperature window that I mentioned, the serpentinization window. There's plenty of mantle potentially within that window, but then we need still large faults, shear zones to allow for water to flow through, to circulate, to stimulate or to allow for the serpentinization and hydrogen generation to occur. The water could come from the surface, so it could be precipitation, but potentially it could also come from deeper down, where you might have water from hydrous minerals that is being released and that can also flow through. And the type of water will also have an effect on the amount of hydrogen or the efficiency of your serpentinization reaction. So that's an interesting question as well. But then the hope that we have is that we might have migration of the hydrogen gas from the area where it's being produced into potentially a hydrogen reservoir, a field like an oil or a gas field, but then filled with hydrogen somewhere maybe in the foreland of one of these origins. And then we can drill that field and produce green energy almost for free, except for the drill, of course, that we have to build. Another option would also be to potentially directly drill into the area where hydrogen is being produced, and you can maybe even pump in water to stimulate the serpentinization and the hydrogen generation. So, but that's something that we will have to see if that works or if it's even a good idea. There's another aspect, because it's this is a very simple schematic that I show you, but there is always a little bit of a problem with hydrogen. It's very reactive as an element. It's something that bacteria like to eat, for instance, or like to consume. And there's also plenty of reactions, so chemical reactions that can use hydrogen, and then it's lost. So one of these reservoirs, if we can find it within maybe something like the 100 and 200 degrees centigrade window, that might be called a hydrogen preservation window, because there we have little biological activity. So that would be a good area for it to accumulate and then to be preserved. So these are questions that need to be answered. But overall, we have a bit of an idea how this might work, but we need to really understand, well, when is the mantle exhumed? When is it in the right temperature range? When do we get the water in there? When are the reservoirs available? And what are the characteristics of the water, and et cetera, and probably plenty of other things as well. But yeah, we're working on this, and so far so good. If we want to explore then this kind of thing in nature, the Mediterranean area seems to be quite nice, because there's plenty of different small basins that have been opened in the past, so rift basins, and that have been closed. So think of, for instance, the Baltics or the Pyrenees or the Alps, where we all have pieces of mantle that are close to the surface, and that could potentially be areas where we would be looking for hydrogen. Especially the Pyrenees, I will show a little bit about that as well. But also in the Alps, there is a ICDP, an International Continental Scientific Continental Drilling Program, I think it's called, where they are drilling into what is called the Ivrea zone, where they actually found hydrogen. And so there seems to be quite some potential there, and who knows, maybe that would be a place to produce it. But yeah, so this is something that we can consider, and there are plenty of other places in this whole Mediterranean belt of the Alpine collision zone that could be of interest. So if we want to conclude a little bit about natural hydrogen, it's very clear that for the system that we are investigating in the models, we need exhumed mantle, but also then water circulation and reservoirs being present all at the right time, and also this temperature effect. So in order to understand that, we need to know how the whole system evolves. And these models that I showed you, they are very useful to get a feeling of the dynamics that could be at play in this kind of thing. And this would all be incorporated in one concept that we can call hydrogen system analysis. Maybe similar to petroleum system analysis or mineral system analysis, where you get all these different aspects together so that you really understand what the sweet spot is for the generation of your resource. The models seem to suggest that rift inversion origins are the best place to look. So they have more capacity for production of hydrogen. There are reservoirs around, and maybe another thing is also that they are relatively easy to access, because if you have to go into a very deep rifted margin area, that can be a challenging environment, whereas the Pyrenees or the Alps, they are somewhat around the corner, if you want. So the Mediterranean indeed is a very good place to look for it, and people are looking. And if you want to know a little bit more about these models, then there is a preprint online of the manuscript that we try to, or an early version of the manuscript that we try to publish. You can ask me some questions as well, and or look at the preprint. But then I would also like to show you a little bit what could be done for actual exploration in the field, to go to maybe use these concepts that we are developing with the models. So I recently went to the Pyrenees to do some exploration over there, and we also plan a project in the Afar Rift in Ethiopia. So the Pyrenees over here, in Ethiopia, and Afar, that's just over there. So the idea would be that in the Pyrenees, we have well, this cross section here in the Western Pyrenees, where we have a piece of mantle that is fairly close to the surface. So maybe this looks somewhat similar to what we have over here. We have large folds, and also here large folds. And in fact, if you go in the field, there are actually there are concentrations of hydrogen in the foreland of the Pyrenees, in this area over here, where this triangle shows the extent of a study that colleagues from France have done, where they were drilling holes in the ground, and then they were measuring the amount of hydrogen basically in the soil. And what they found is that there are big faults there in the foreland of the Pyrenees, which seem to allow hydrogen to come up from the depth. So it's very interesting. So we also went there and did a little bit of that. But the more important thing that we did is that we brought a mass spectrometer to a certain area to measure the amount of hydrogen in the field there, in an area where there was plenty of hydrogen found in the past. And that was a pretty interesting thing to do. But the key thing was that we went to bubbling springs, or springs in general, in the area. There's plenty of geothermal springs or baths, etc., in the area. So this is an old bath location, and it's full of little bubbles that you can hopefully see here. You can capture these and you can analyze them with geochemical analyses, and then you can try to better understand what's in the gas. So is there hydrogen? And in fact, we found hydrogen in a couple of places, quite a lot compared to the background hydrogen that you would expect. And then you can try to understand with isotopes where it comes from. This is not conclusive, so we are actually going back to the Pyrenees to do more sampling. But yeah, it seems to fit with the idea that we have, that I showed you with the models, that hydrogen is being produced and it might just come from the mantle, which might indicate an active system. And then potentially there could be these reservoirs that we could drill. And so people are actually nowadays looking for these reservoirs, trying to find them. And another project that we're trying to start is in a rifting setting. So it's not the ideal setting perhaps, but still we want to look into Afar. Afar is the triple junction between the Red Sea Rift, the Gulf of Aden Rift, and the East African Rift system, where they all come together. There's a hotspot there there's plenty of basaltic magmatism and volcanism, and in some sense it's very similar to Iceland. And the interesting thing actually in Iceland is that they have lots of geothermal plants where they also have emissions of hydrogen that they found recently, because they started to measure, and yeah, they actually get a lot of hydrogen out of their system. So there is something going on, and it can be the mantle, but it could also be all the basalts, because the basalts, they are also full of olivine and pyroxene minerals, and they can also serpentinize. So it doesn't have to be necessarily mantle rock. It could also be other sources. So we want to go into that area, and what is shown here on this map is those are deep boreholes that we can measure for heat flow data. So that's important for geothermal analysis, but also you can use it for your estimation of the serpentinization window. So this temperature range in which serpentinization is productive. And so that would be a nice constraint for hydrogen. And we're also talking about taking samples or measuring hydrogen in the field over there. And this data, this heat flow data, is very important because there is no heat flow data at all in this area, in this part of the world, which is well known for being a highly volcanic area where we can potentially do geothermal energy production. And the hope is that this works, and then we can link it up with International Continental Drilling Program, a project that's planned in the north of this area, where we can link this up. And so this would be a very nice thing for the future, and we can then again use this data for the modeling and to do better, or to get better models, better results, better constraints on this kind of system. And I think that's the end of the talk. Here's a little video again. So thank you very much for your attention. And if you have any questions, let me know. Thanks.